Hello everyone, I'm Haibo Cheng from Peking University. Here I give a talk on incrementally updatable honey password vaults. Password vaults, also known as password managers, are recommended for password management. A user can store multiple passwords in a vault and further set up master passwords to encrypt the vault. The subtext is usually stored on an online service or sync, so that a user can retrieve the passwords, the website passwords on any client by only remembering the master password. But the password vaults suffer from a significant threat. An attacker may steal the storage file from the online service. Then she can carry out a guessing attack against the master password. Since the master password is human memorable, it may be easily guessed. In addition, traditional encryption yields failure or random jump for incorrect guesses. Then the attacker can efficiently retrieve all website passwords. Honey password vaults are proposed to address these issues. This technique can generate decoy vaults for incorrect keys, so that the attacker cannot distinguish the real one and have to do online verification, which can be easily prevented. The state-of-the-art honey vault schemes leverage honey encryption for decoy generation. The passwords are first encoded to a uniform bit string by an encoder and then will be encrypted. The encoder is designed according to the password vault distribution so that a random bit string will be decoded to a plausible-looking vault. An open problem for honey password vaults is how to achieve update security if the user adds or changes a website password. The current honey vault schemes do a full update for the subtext, even if only one password is changed. This yields an independent new version for each decoy vault. Thus, an attacker can easily distinguish the real vault according to the similarity between the old and the new versions. To carry out this attack, the attacker only needs the old and new version of the subtext. The old subtext is usually stored along with the current version as a backup. This means the threat is practical, not just a theoretical one. We first propose a generic construction and an incremental update mechanism for honey vaults, which achieves update security. Further, we instantiate our construction, which can generate more plausible-looking decoys. In addition, we formally investigate the optimal strategy for distinguished decoys and propose practical attacks to evaluate the honey vault schemes. Our construction for password vaults is simple. We think the user generates the password one by one, so that the probability of a vault is the product of the conditional probability of passwords. Then we only need to estimate the conditional probability of a new password and several given old one. Based on the simple construction, we propose the conditional encoder, which can encode a new password and several old ones. The conditional encoder is designed according to the conditional probability model by Cheng et al.'s transformation. Then the vault can be encoded password by password. The bit string of a vault is a concatenation of the bit string of passwords. With the conditional encoder and a prefix keeping encryption scheme, we can provide an incremental update mechanism to add a new password. We first encode the new password and add the password bit string to the vault bit string. To delete an old password, we mark the password as deleted, but do not change the subtext. To change an old password, we encode the new password, add the password bit string to the vault bit string, and update the password index for the corresponding account. The conditional encoder guarantees that the old byte string is a prefix of the new byte string. The prefix keeping encryption scheme for the guarantee that the old subtext is a prefix of the new subtext. Thus, attacker with two versions of the subtext degenerates to an attacker only with the current version. For each decoy words, the passwords in the new version are the same as those in the old version, except the changed ones. This means our incremental update mechanism achieves update security. To instantiate our construction, we propose a new conditional probability model for password words. The basic idea is simple. A user generates a new password by reusing an old one or not. For reusing case, we design a simple single similar password model to capture how a user reuse an old password. For the second case, we use a Markov model to capture how a user creates a brand new password. Then we use the unreused probability to capture the probability of the second case. Another important question for Honeywood's research is how to evaluate the indistinguishability of decoys. To answer the question, we formally investigate the optimal strategy of distinguish real and decoy words. The optimal strategy is ranking the word by the conditional probability of being real and the given subtext. The conditional probability for a word is proportional to the real to decoy probability ratio. But the real probability cannot be precisely calculated. So we estimate the ratio on the single password distribution and password reused features, and then propose practical attacks. The experimental results show that our attack is more effective than the state-of-the-art attack against the existing schemes. No attack achieved more than 58% distinguished accuracy against our scheme. This is close to 50% for the perfect scheme. Compared with the current scheme, our scheme brings 2.8 to 7.5 times online cost to attackers. Note that the online guessing can be easily prevented. This is a great improvement on security. Our work may also benefit other research topics. For example, the incremental update mechanism may apply to other applications using horn encryption. The probability model design for passwords and password words may be used for password guessing. We leave this as future work. Thank you.